हेलो एवरीवन, वंस अगेन वेलकम टू आवर चैनल बीट द नीड। और ये आपकी क्लास 11th यूनिट 3 जो पीरियोडिक एलिमेंट्स थे उस चैप्टर का पार्ट 2 ऑडियो बुक का है। सो चलिए स्टार्ट करते हैं, टाइम नहीं वेस्ट करते हैं। 3.7 Periodic Trends in Properties of Elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 non-metals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of non-metals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends? And how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of the atom. In the section, we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. 3.7.1 Trends in Physical Properties. There are numerous physical properties of elements such as melting points, boiling points, heat of fusion, vaporization, energy of atomization, etc., which show periodic variation. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. A. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than the measuring the radius of a ball. Do you know why? Firstly, because the size of an atom, that is 1.2 angstrom, that is 1.2 into 10 to the power minus 10 meter in radius, is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between the two atoms when they are bound together by a single bond in covalent molecule, and from this value, the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule, that is Cl2, is 198 pm, and half the distance, 99 pm, that is picometer, is taken as the atomic radius of chlorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 pm. Hence, the metallic radius of copper is assigned a value of 128 pm. For simplicity, in this book, we use the term atomic radius to refer for both covalent or metallic radius depending on whether the element is a non-metal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of few elements are listed in table 3.6. Two trends are obvious. We can see the table atomic radii 3.6a and 3.6b. One is atomic radii pm down a family, and one is atomic radii pm across the periods. We can explain these trends in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in figure 3.4a for the elements of the second period. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of periodic table, the atomic radius increases regularly with atomic number as illustrated in figure 3.4b. For alkali metals and halogens, as we descend the groups, the principal quantum number increases and the valence electrons are farther from the nucleus. This happens because the inner energy levels are filled with electrons which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii values are very large. In fact, radii of noble gas should be compared not with the covalent radii but with the van der Waals radii of other elements. See figure 3.4a and figure 3.4b. Both are variation of atomic radius with atomic number across the second period and variation of atomic radius with atomic number for alkali metals and halogens. B. Ionic radius. The removal of an electron from an atom results in the formation of cation, whereas the gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, the ionic radii of element exhibit the same trend as the atomic radii. A cation is smaller than its parent's atom because it has fewer electrons, while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, the ionic radius of fluoride ion is 136 pm, whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for Na ion. When we find some atoms and ions which contain the same number of electrons, we call them isoelectronic species. For example, O2 negative, F negative, Na positive and Mg2 positive have the same number of electrons, that is 10. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. An ion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. C. Ionization enthalpy. A quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. In other words, the first ionization enthalpy for an element X is the enthalpy change, that is delta H, for the reaction depicted in equation 3.1. Here you can see the equation X gives out X positive plus E negative. The ionization enthalpy is expressed in unit of kilojoule per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in equation 3.2. It is X positive gives out X2 positive plus electron. Energy is always required to remove electron from an atom and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positive charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second and so on. The term ionization enthalpy, if not qualified, is taken at the first ionization enthalpy. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in figure 3.5. Here is the figure. The periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and very stable electronic configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies can be correlated with their high reactivity. In addition, you will notice two trends. The first ionization enthalpy generally increases as we go across a period and decreases as we descend in group. These trends are illustrated in figures 3.6a and 3.6b. I will show the diagram respectively for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors, that is the attraction of electrons towards the nucleus and second, the repulsion of electrons from each other. The effective nuclear charge experienced by the valence electron in an atom will be less than, first see the diagram, 3.6a and 3.6b. The actual charge in the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening cold electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electron experiences a net positive charge which is less than the actual charge plus 3. In general, shielding is effective when the orbitals in the inner shells are completely filled. This situation occurs in the case of alkali metals, which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly and the ionization enthalpy increases across a period. As we go down a group, the outermost electrons being increasingly farther from the nucleus. There is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge and the removal of the outermost electron requires less energy down a group. From figure 3.6a, you will also notice that the first ionization enthalpy of boron is slightly less than that of beryllium. Even though the former has a greater nuclear charge, when we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during the ionization of boron is a p electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smallest first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, their 2p electrons resides in different atomic orbitals, that is Hund's rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the fourth 2p electron from oxygen than it is to remove one of the 3 2p electrons from the nitrogen. D. Electron gain enthalpy. When an electron is added to a natural gas's atom X to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion as represented by equation 3.3. X gives a plus, electron gives out X negative. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements have very high negative electron gain enthalpies because they can attain a stable noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpies of elements is less systematic than the ionization enthalpies. As a general rule, electron gain enthalpy become more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group, because the size of the atom increases and the added electron would be farther from the nucleus. This is generally the case. Table 3.7 you can see. I will show you. However, electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding element. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n is equals to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equals to 3 quantum level, sulfur or chlorine, the added electron occupies a larger region of space and the electron-electron repulsion is much less. This is table 3.7, electron gain enthalpies of some main group elements. E. Electronegativity. A qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scales of the electronegativity of elements via Pauling scale, Mulliken-Zaff scale, Allred-Rockow scale have been developed. The one which is the most widely used is the Pauling scale by Linus Pauling, an American scientist in 1922 assigned arbitrarily a value of 4 to fluorine, the element considered to have the greatest ability to attract electrons. Approximate values for the electronegativity of a few elements are given in table 3.8a. I will show you. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that you will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down a group, say from fluorine to astatine. In the periodic table, how can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right but increase down each group? The attraction between the outer or valence electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases on the same account. Electronegativity values decreases with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Knowing the relationship between the electronegativity and atomic radius, can you now visualize the relationship between the electronegativity and non-metallic properties? See this 3.7, the periodic trends of elements in the periodic table. Then 3.8a, electronegative value across the periods. Table 3.b, electronegativity values on Pauling scale down a family. Non-metallic elements have a strong tendency to gain electrons. Therefore, electronegativity is directly related to that non-metallic properties of elements. It can be further extended to say that electronegativity is inversely related to a metallic properties of elements. Thus, the increase in electronegativities across a period is accompanied by an increase in non-metallic properties or decrease in metallic properties of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in non-metallic properties of elements. All these periodic trends are summarized in figure 3.7. That is the figure 3.7. Now, 3.7.2 periodic trends in chemical properties. Most of the trends in chemical properties of elements such as diagonal relationships, inert pair effect, effect of lanthanoid contraction, etc. will be dealt with along the discussion of each group in later units. In this section, we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements from lithium to fluorine. A. Periodicity of valence or oxidation states. The valence is the most characteristic property of the elements and can be understood in terms of their electronic configuration. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to 8 minus the number of outermost electron as shown below. Nowadays, the term oxidation state is frequently used for valence. Consider the two oxygen-containing compounds OF2 and Na2O. The order of electronegativity of the three elements involved in these compounds is fluorine is greater than oxygen is greater than sodium. Each of the atoms of fluorine with outer electronic configuration 2s2 2p5 shares one electron with oxygen in the OF2 molecule. Being highest electronegative element, fluorine is given oxidation state -1. Since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration 2s2 2p4 shares 2 electrons with fluorine atoms and nearby exhibits oxidation state +2. In Na2O, oxygen being more electronegative accepts 2 electrons, one more each of the two sodium atoms, and thus shows oxidation state -2. On the other hand, sodium with electronic configuration 3s1 loses 1 electron to oxygen and is given oxidation state +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by atom on the basis of electronegative consideration from other atoms in the molecules. Some periodic trends observed in the valence of elements, hydrides and oxides, are shown in table 3.9. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. See the table 3.9. Periodic trends in valence of elements as shown by the formulas of their compounds. There are many elements which exhibit variable valence. This is particularly characteristic of transition elements and actinoids, which we shall study later. B. Anomalous properties of second period elements. The first element of each of the group 1 and 2 and group 13 to 17 boron to fluorine it is differs in many respects from the other members of their respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, from compounds with pronounced covalent character. The other members of these groups predominantly form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, that is magnesium and aluminium respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of a group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large charge, radius ratio, and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbitals 2s and 2p available for bonding, whereas the second member of the groups have 9 valence orbitals 3s, 3p, 3d. As a consequence of this, the maximum covalency of the first member of each group is 4. Example, boron can only be formed Bf4 whole negative, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminium AlF6 whole 3 negative. Furthermore, the first member of p block elements displays greater ability to form p-pi multiple bonds to itself. Example, C-pi double bond C-pi, C triple bond C, N double bond N, and triple bond N. And to the other second period elements, example, C double bond O, C double bond N, C triple bond N, and double bond O, compared to subsequent members of the same group. 3.7.3 Periodic Trends and Chemical Reactivity. We have observed the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and valence. We know by now that the periodicity is related to electronic configuration. That is, all chemical and physical properties are manifestation of the electronic configuration of elements. We shall now try to explore relationships between these fundamental properties of elements with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase, with some exceptions as outlined in section 3.7.1a, and electron gain enthalpies become more negative across a period. In other words, the ionization enthalpy of the extreme left element in a period is the least, and the electron gain enthalpy of the element on the extreme right is the highest negative. Note: noble gases having completely filled shells have rather positive electron gain enthalpy values. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali metals is exhibited by the loss of an electron, leading to the formation of a cation, and at the extreme right among halogens shown by the gain of an electron forming an anion. This property can be related with reducing and oxidizing behavior of the elements, which you will learn later. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element which is highest at the extremely left decreases, and the non-metallic character increases while moving from left to right across the period. The chemical reactivity of an element can be best shown by its reaction with oxygen and halogen. Here we shall consider the reaction of the elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is the most basic, example Na2O, whereas that formed by the element on extreme right is the most acidic, example Cl2O7. Oxides of element in the center are amphoteric, example Al2O3, As2O3, or neutral, example are CO, NO, N2O, etc. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas the neutral oxides have no acidic or basic properties. Among transition metals, that is 3D series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals, that is 4F series. The ionization enthalpies are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, that is with the exception in some third period elements as shown in section 3.71d. In electron gain enthalpies in the case of main group elements, thus the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which you will learn later. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. Summary: in this unit, you have studied the development of periodic law and periodic table. Mendeleev periodic table was based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers in 7 horizontal rows, that is periods, and 18 vertical columns, that is groups of families. Atomic numbers in a period are consecutive, whereas in the group they can increase in a pattern. Elements of the same group have similar valence shell, electronic configuration, and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configuration. These are S, P, D and F block elements. Hydrogen with 1 electron in the first S orbital occupies a unique position in the periodic table. Metals comprise more than 78% of known elements. Non-metals which are located at the top of the periodic table are less than 20 in number. Elements which lie at the border line between metals and non-metals, example silicon, germanium, arsenic, are called metalloids or semi-metals. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity, and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increases across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down a group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is the highest at two the extremes of a period and is lowest in the center. The reactivity on the left extreme of a period is because of the ease of electron loss or low ionization enthalpy. High reactive elements do not occur in nature in free states. They usually occur in the combined form. Oxides formed of the elements on the left are basic and the elements on the right are acidic in nature. Oxides of elements in the center are atmospheric or neutral. Chapter done. See you in the next chapter. And आप लोगों के जैसे सजेशंस आ रहे हैं कमेंट बॉक्स में, जिन चैप्टर्स के लिए ज़्यादा आप लोगों को रिक्वायरमेंट है इस टाइम में, आप मुझे कमेंट सेक्शन में बता दीजिए. आई विल मेक देम फर्स्ट. सो जो अभी तक मेरे पास सजेशंस आ चुके हैं, मैंने उन पे वर्कआउट करना ऑलरेडी स्टार्ट कर दिया है. सो थैंक यू सो मच एवरीवन. प्लीज शेयर दिस विद योर फ्रेंड्स एंड इफ इट हेल्प्स यू, सो प्लीज लाइक इट. थैंक यू सो मच.